In this video, we will simulate Brownian motion using a Brownian bridge. This is different to the first video, simulating Brownian motion, where we built up the path sequentially. The essence of the Brownian bridge method is that we fix the endpoints and simulate the midpoint. We continue to do this, getting a more and more granular path, as the animation shows. Looking more closely at this example, we start the Brownian bridge at time t1 at the point A, and it finishes at time t2 at the point B. We want to know what the distribution of a Brownian motion is at an intermediate point t, conditional on the path being tied down at times t1 and t2. Luckily, we know the distribution. It wouldn't surprise you to hear that it is normally distributed. But what is the mean and variance? The mean is linear between A and B, following this red line as t goes from t1 to t2. The variance is 0 at t1 and also 0 at t2. It is maximum when t is midway between t1 and t2. So now we have all that we need to simulate Brownian motion using a Brownian bridge. We pick a starting point 1 and simulate the second point. We learnt how to simulate normal random variables in the first video, simulating Brownian motion. The third simulated point occurs at the midpoint of t1 and t2. This is where we use the formula for the distribution of the Brownian bridge to get the mean and variance of the required point. Now we halve the interval size and simulate a Brownian bridge between the points 1 and 3. This gives us point 4. We then simulate a Brownian bridge tied down to points 3 and 2. This gives us point 5, and so on. Each iteration we create a more granular path with half the interval size. This is all you need to know in order to use the Brownian bridge for simulating Brownian motion. Remember, if you like the content, please subscribe to my channel and hit the like button. In the rest of the video, we will derive the mean and variance of the Brownian bridge using Bayes' theorem. We will start a Brownian motion at the left point A of the Brownian bridge. The probability density of a Brownian motion starting at A is that of a normal distribution with mean A and variance t, the time elapsed. This probability density is the same as that of a standard Brownian motion, except we have an x minus a in the exponent instead of just an x. Recall Bayes' theorem, which allows you to calculate the probability of an event A, conditional on B, in terms of the probability of B, conditional on A. The probability of A given B, the first term here, is by definition the probability of A and B divided by the probability of B. We can then swap around A and B to get another expression for the probability of A and B in terms of the probability of B given A. This gives you the last expression. Why is this useful? Well, depending on what events you choose for A and B, sometimes it is easier to calculate B given A than it is to calculate A given B. We take the event A to be the path being in a small interval dx at time t. And we take the event B to be the path finishing at point B at time t2. Strictly speaking, we should say a small interval around B, since the probability of hitting exactly any point is 0. We are being a bit cavalier about this. The third equation is the one we will calculate. It is much easier for us to calculate B given A, since this follows the natural flow of time. We want to know the probability of finishing at B at time t2, given that we are at some point x at time t. We will use the fact that Brownian motion increments are 1. Independent, and 2. Normally distributed, with mean equal to its current position and variance equal to the time period. So if you are at point x at time t and finish up at B in an interval equal to t2 minus t, this probability is normal, centered at B minus x, with variance t2 minus t. The next term is just the probability of being at x at time t, starting at point A at t1. This is also normal, centered at x minus a, with variance t minus t1. Finally, the last term, the denominator, is the probability of being at b at time t2, with the Brownian motion starting at point A at t1. This is normal, centered at b minus a, with variance t2 minus t1. Let's put together all the terms outside the exponent by multiplying them together. And now just add the exponents, and we also divide by dx to get the probability density. The term to concentrate on is the exponent. We will put it all under one denominator. We want to complete the square in x, that is, write the numerator as x minus some constants, all squared, plus a compensating term not containing any x's. After expanding the terms containing x, we see that the coefficient of x squared is actually t2 minus t1 all squared. Next, we look at the coefficient of x, which comes from this term here and this term, multiplied by t2 minus t1 on the outside. Now the trickier bit is to deal with the constant terms. We have an existing term from the first bracket in a squared, and a second term in b squared from the second bracket. We have also added a new constant from completing the square in x, which we subtract, and then we add on the existing constant. Luckily for us, the last two lines cancel each other out. Let's put back the exponential and the constant multiplier to get the final probability density. If we compare this with the normal density function, we see that the mean mu is a time-weighted average of a and b, and the variance sigma squared is as given. I hope you enjoyed this video on the Brownian bridge. Remember, if you like the content, hit the like and subscribe button, and I look forward to making more content like this in the future.